Of the two parts of the fundamental theorem of calculus, the one that's written second here tends to be the one that's a little easier for people to comprehend. This part is sometimes referred to as the evaluation part because it's the one that tells us how we can evaluate a definite integral. The first part often takes a little more work to wrap your head around. So we're going to do a few exercises here to help us understand what it means that if we have this function g of x defined by this integral from a to x of f of t, then g prime of x is equal to f of x. So we're told that each expression below defines a function g in terms of an integral. And for each expression, we should begin by using part 2 of the fundamental theorem to rewrite each integral as a difference rather than as an integral. So let's do that for problem number 1. Here we have the integral from 3 to x of little f of t dt, and the evaluation part of the fundamental theorem tells us that we can rewrite that as big F, the antiderivative of little f, of the upper limit of integration x minus big F of the lower limit of integration 3. Okay, straightforward enough. Now part B, use the result of part A to identify what variable g is a function of. Well, if g is equal to f of x minus f of 3, then g is a function of x. That t that was originally in the integrand just goes away after we find the antiderivative because we're plugging in these limits of integration. And finally, C, find g prime by taking the derivative of the difference we wrote in part A with respect to the variable we identified in part B. So if we take the derivative of the left side, we get g prime of x. And if we take the derivative of the right side, we get capital F prime of x minus the derivative of f of 3, but f of 3 is just a constant, so that will be 0. And remember that capital F was an antiderivative of little f, so taking the derivative of the antiderivative of little f just gives us back little f. So g prime of x equals f of x, which is that conclusion of the first part of the fundamental theorem. Let's try it again with some different letters. In number 2, we have the integral from 1 to t of little f of x dx. So the evaluation part of the fundamental theorem tells us that this will be capital F of t minus capital F of 1. So the only variable there is t. That tells us that g is a function of t. Again, we see that g is a function of the variable that showed up in the limit of integration, not the variable that showed up in the integrand. So g prime of t will be just capital F prime of t minus 0 again, and that will be just f of t. So again, g prime, the derivative of the function defined by the integral, is equal to the integrand evaluated at the upper limit of integration. And you can do number 3 on your own to make sure you've got the hang of that. So what we've looked at so far tells us what to do if we see a problem that looks like this. That just looks terrible. I don't want to have to think about finding an antiderivative, but I don't have to because the fundamental theorem tells me that if I have the derivative of this function, which goes from a constant to the variable that I'm differentiating with respect to, of some integrand, the answer to that is just going to be the integrand with the upper limit of integration variable plugged in. Now, you can't go too crazy and just stop thinking altogether when you see the derivative of an integral, because remember, This depended on the lower limit of integration being a constant and the upper limit of integration being the variable that we're taking the derivative with respect to. So we're going to work through a few more exercises which don't exactly match that pattern and see how we can deal with that. So let's start with number 4. Pause briefly and see what's different in number 4 from the previous ones. All right, in number 4, we've got a variable as the lower limit of integration and a constant as the upper limit of integration. But we're going to follow the same steps we followed in the previous ones and just see what happens. So we were told evaluate using the evaluation part of the fundamental theorem. So that'll be capital F of 6 minus capital F of z. And we see that the variable that appears there is still a z, even though it was in the bottom. And taking the derivative of both sides, we get g prime of z. And here we get the 0 first, and then capital F prime of z. So in this case, we get g prime of z equals negative little f of z. That should really be no surprise because we could have rewritten this integral we were given at the beginning as the negative of the integral from 6 to z. Okay, moving on to number 5. Pause and see what's a little different there. In this case, both of the limits are constants. So you can think about what you expect to have happen. But let's just follow the same steps we've been following in the other ones and see what does happen. So using the evaluation part of the fundamental theorem, capital F of 4 minus capital F of negative 1. And we have no variable in that expression. So this could actually be a function of any variable other than y. So we can put anything we want to there. So let's call it x. And taking the derivative of both sides, g prime of x, both of those terms on the other side are constants, so g prime of x is just 0. We can spend a minute thinking about why that makes sense. The integral that we had over here was actually not much of a function. It was an integral from negative 1 to 4, so it always represented the same area. So this is a constant, meaning g of x is a constant function whose derivative must be 0. Moving on to number 6. As we look at the limits of integration here, we have a constant on the bottom, but on top we don't have just a single variable, we have a function of a variable. So you might want to pause and think about how you think that might turn out, and then go through those steps that we've been going through in the others. So step 1, evaluate using the evaluation theorem. That gives us capital F of the upper limit, cosine of y, minus capital F of the lower limit, 1. And when we want to see what variable g is going to be a function of, well, y is the only variable over here, so g is a function of y. And to find g prime of y, I take the derivative of capital F of cosine of y. So this is a mother and baby situation. So I have capital F prime of the cosine of y times the derivative of the cosine, which is minus sine, and then minus 0 again for the derivative of f of 1. So simplifying a bit as we did in the others, g prime of y equals little f of cosine of y times minus sine of y. So the moral of the story here in number 6 is that if we're taking the integral from a constant to a function of some other variable, the chain rule is going to come into play. Let's look at an example of that. So if I had just made a tiny little change to this example that I had done before, and say I'd had ddr of the integral from 5 to r squared of this mess, I would have gotten the integrand, but not with just r plugged in, for q, but r squared plugged in for q, and I would have had the derivative of the r squared. So I can still apply the fundamental theorem of calculus first part if I see a problem like this. I just have to remember the chain rule. You can try to write down what that would be. Hopefully you got g of f of x, the integrand with the function plugged in for the variable, times the derivative of the function that was the limit of integration. So there's one problem left here. Try that one on your own. This one has a function in both spots. Think about how you imagine that's going to turn out based on that first part of the fundamental theorem of calculus, and then work through the steps we've worked through in the other problems and see if you're right.